So now we're going to talk about why things float and one of my favorite historical people. Now, for some of you that are taking Naval Arc, I know there is a professor that he once told me that he teaches all the students that little mermaids hold the ships up, and that's why they float. I'm sorry to be the bearer of bad news, but that's not exactly true. So what we're going to do is we're going to talk about Archimedes. And as I said, Archimedes was one of my favorite historical people. Archimedes was a brilliant Greek scientist, mathematician from the city of Syracuse, which is basically Syracuse, not New York, but Syracuse on the island of Sicily. He was a genius. He lived from 287 BC to about 212 BC. The guy basically invented integral calculus. The Romans ended up sieging Syracuse, and they were going to enfold it into the empire, and they were scared crapless of this guy. During the siege, anytime they saw an old white bearded man on the walls, they hid behind their shields. It's been written in antiquity that he developed this kind of a steam catapult gun that they would shoot at the Romans, that they came up with a big claw that would flip ships in the water near the city. There's also the heat ray death gun that they've talked about, which I know there's been 2 episodes of Mythbusters that have both busted the myth that this could possibly have worked and also proved that it could possibly have worked. Needless to say, the guy was really smart. He invented integral calculus. Just to show you how scared the Romans were of him. Now, mind you, the Romans, their penalty for disobeying an order was death. They were commanded to capture this guy when they finally stormed the city. They stormed into his office, and they just killed him. Reportedly, his last words were along the lines of, "Don't disturb the sand," because they would use sand on tables to draw, and he was drawing circles, and that's his reported last words. Now, there are stories about Archimedes that you may have heard of, the entire thing of he needed to figure out if King Hero's crown was really gold, and one day he got into the bathtub that was all full, and the water spilled out of it, and he popped up and said, "Eureka," which was Greek for "I have it," and that's how he figured out everything that we're going to talk about today. Great story, completely not true at all. Anyway, let's get into what Archimedes' principle is. So let's look at, we've got a picture here of a body that I've got submerged underwater. And Archimedes' principle is basically broken up into 2 laws. And they basically kind of say the same thing. So we'll just cut right to the chase. But if I sit here and I look at my body, it doesn't matter what I have. I have surface 1, surface 2. Surface 1 is the upper surface. Surface 2 is the lower surface. And I'm going to have forces on both of these surfaces. So what's the force going to be? Well, we can calculate out the hydrostatic force because we know how we do that. Because the fluid is going to be pushing on an object, and it's going to be pushing with the weight of whatever the depth of the object is times the specific weight of the fluid. So, in sense, all of our forces are going to be acting perpendicularly to the object. So when we look at things along surface 1, we have all those forces that are going to be acting in a downward or a negative direction. On the bottom, I'm still going to have the same kind of force because I'm still going to have whatever it is, gamma to that height to where that force is, but now since it's on the bottom, it's actually pushing up. So we have some kind of positive force. And so there is going to be a difference in these 2 forces because the force on the top, since it's closer to the surface, will have less hydrostatic force pushing down, but the force on the bottom, being a little bit deeper, is going to have more hydrostatic force pushing up. And so what this force, this difference between the 2 gets termed as, is what we call buoyancy. And that's represented as F sub B is the force of buoyancy. And so the force of buoyancy is going to be that vertical force on surface 2 minus whatever's on surface 1. And so that difference is going to be this net upward force that's going to be pushing on the bottom and trying to push this thing up that we have submerged in water. So that would be the first law. Well, let's look at the second law, because we're just talking about forces here. We're going to look at the second one, and this is probably a little bit more direct to what we're doing. So I know this force of buoyancy is this difference between these two forces. So if I look at this, and so what I want to do is, okay, well, I'm going to do the buoyant force, and I want to look at things and go, okay, well, I'm going to integrate over the body, over the entire body. And so I'm going to have, looking back at the first law, well, the pressure of 2 minus the pressure at 1 times the differential area, the horizontal differential area, the horizontal element. And so basically this gives me that FV2 minus FV1. So I know what the pressure at 2 is going to be. Well, the pressure at 2 is going to be negative gamma times Z2. And then I know that the pressure at 1 is going to be negative gamma times Z1. So I've got that difference, since I'm doing the difference in the pressure of Z1 minus Z2. And still multiplying it by that differential element and still taking this over the entire body. Now, if I look at it, well, Z1 minus Z2 is kind of the height of this body. And so if I've got the height of the body, and then I'm doing it over this horizontal area element, and I integrate that over the body, what is that going to give me? That's going to give me the volume of the body. So what I'm going to end up with is the force of buoyancy is going to equal the specific weight of the fluid times that volume of the body. Now, that negative ends up, as we're doing all the integrations, that ends up falling out from our equation, which is fine because we're going to get an upward pushing force. And so in general, this is the equation for the force of buoyancy. Now, this only works when we have something submerged in fluid, so it's actually, what I like to do is say submerged. Because really, if I've got part of the body that is not submerged underwater, it's not providing any of that buoyant force. So if I look at it, this is how I can calculate out whether or not something's going to float. So if I look at the force of buoyancy, and then I'm going to compare it to the weight of the object. So if the buoyant force is greater than the weight, it's going to ascend in the fluid, and it's going to float. If the buoyant force is less than the gravity, the body is going to sink. And then if the buoyant force is equal to the mass times the gravity, it's going to stay just right where it is in the fluid. So if we think about it, if I throw a chunk of wood in water, well, the wood is less dense than water, and that's why it will float. If I chunk a hunk of metal in the water, the metal is much denser than water, and that's why it sinks. So this is basically how all that stuff works. So the question is, we look out, why does a ship like the Kennedy float? Because it's made of metal, and that's more dense than water. Now, of course, I can't have you respond to me here, and I'll just give you the answer. That's because the Kennedy is mostly not metal. It's air inside. And so the air is much less dense than the water. This is actually kind of how they measure how heavy a ship is, because they can't really put it on a bathroom scale and go, yeah, that weighs 120 some tons. They take a dry dock and they bring the ship in and they look where the water level is, and they can calculate out what the buoyant force on that ship is. So this is probably one of the simpler equations that we're going to have, but I mean the main thing to remember is submerged force. Because what's going to happen is if you drop something into a fluid and push it down under that's less dense than water, it's going to keep going up until the volume submerged will stabilize with the buoyant force. So it naturally wants to get to this point where the buoyant force is equal to the mass times the gravity. One other thing to keep in note that some people don't think about when they're calculating out things, if I've got a block of iron sitting at the bottom of the ocean, I go, okay, well, say the iron weighs 60 pounds pushing down, and if you're trying to calculate things out, it's like, okay, well, I have a normal force of 60 pounds pushing up. That's not true, because since you're displacing the fluid, you still have a buoyant force on that block of iron trying to push it up. And so that's one thing that you have to watch out for, is you've got to realize that, mg is going to be the buoyant force plus the normal force coming up. Now, if this is completely on there and there's absolutely no water in there whatsoever, there's going to be things going on with the buoyant force. But the thing to remember is, once again, submerged is the key.